Take question 13 of exercise 6.3. Find points on the curve an ellipse x square by 9 plus y square by 16 equals to 1 at which the tangents are parallel to x-axis, parallel to y-axis. Okay, so let us solve it. Solution. Given curve is x square by 9 plus y square by 16 equals to 1. Okay, we have to find points on this curve. This is ellipse. Points on this curve where tangents will be parallel to x-axis and parallel to y-axis. Slope of x-axis is 0. Slope of y-axis is infinitive, not defined. That is, slope of normal will be equals to 0 because minus 1 upon infinity equals to 0. So, by taking these two conditions, we have to find the value of x and y, that will be the points on the ellipse where tangents will be parallel to x-axis, parallel to y-axis. So, first of all, differentiate it. So, for that, slope of tangent, the slope of tangents to the curve is given by, to the curve at xy is given by dy upon dx. So for that is given by dy upon dx at xy. For this we have to find derivative from 1. Equation 1. So differentiate with respect to x on both sides. Now we have to find dy by dx from here. Side of 1. We get, differentiate it, 2x upon 9 plus, differentiate it with respect to y, x, so 2y upon 16 and also dy by dx equals to 0, right hand side with respect to 0. So from here we see that dy upon dx, this is equals to minus of (16x) upon 9y. Okay, so transfer this on right side, 2 to cancel. So 16x minus 16x upon 9y. This is the derivative. Okay, so slope is given by this, implies dy upon dx at xy equals to minus 16x upon 9y. This is slope at xy. Okay. Now, slope of tangent. Slope of tangent. Now, tangents are parallel to x-axis. Now, first, tangents will be parallel to x-axis if slope of tangent is 0. That is slope of x-axis implies minus 16x upon y equals to 0, which gives x equals to 0. So, for x equals to 0, from the equation from 1 x square upon 9 plus y square upon 16 equals to 1 implies 0 upon 9 plus y square upon 16 equals to 0 implies y equals to plus minus 4. Y equals to plus minus 4. Y may be plus 4 minus 4. That is, points are 0 plus 4, 0 minus 4. 0 plus 4 and 0 minus 4. Where tangents will be parallel to x-axis. Okay, this is first part of the question. Clear? Now, second part is this. Tangents will be parallel to y-axis, that is vertical. That means slope of vertical line is infinitive, that is slope of tangent is infinitive, so slope of normal is 0. Now, and so for second part, tangent will be parallel to y-axis if slope of tangent, slope of normal is 0. Slope of normal is equals to 0. That is, normal is minus 1 upon slope of tangent, minus 16 upon x upon 9y is equals to 0. Slope of normal minus of 1 upon slope of tangent is equals to 0. This implies 9y upon 16x equals to 0 implies y equals to 0. Here y equals to 0. So, for y equals to 0, from 1 x square upon 9 plus y square upon 16 equals to 0 implies y equals to 0. That is x square upon 9 equals to 1. X square upon 9 plus y square upon 16 equals to 1. That is y equals to 0 means x square upon 9 equals to 1 implies x equals to plus minus 3. Plus minus 3. That is y equals to always 0 and x equal to plus 3 and minus 3. That is points are 3, 0 and minus 3, 0 where tangents will be parallel to y-axis. So these are 2 points where tangents will be parallel to y-axis. So these are the solution of question 13 of exercise 6.3. Okay. Take another question 17. That is, find points on the curve y equals to x cube at which the tangent slope of the tangent is equal to the y coordinate of the point. Means if this is curve, then we have to find this point where slope of this tangent is equals to its y coordinates. Suppose point is xy, then y coordinate is y. Slope of this tangent will be equals to y. Slope of the tangent is given by dy by dx, where y is equals to fx is the curve. So we will take derivative, that is slope of the curve at this point is equals to y, and solving we can get the points. Okay. So given curve is y equal to x cube. Here solution. Given curve is y equals to x cube. Okay. Let xy be the point. Required point at which tangents to the curve is given by dy upon dx at xy. So differentiate y equal to x cube implies differentiate it 3x square implies dy by dx at xy is equals to 3x square. This is the required point at which slope of tangent to the curve is given by this. That is, this is the slope of the tangent. Okay. Now according to question, slope of tangent equals to y coordinate of point. That is slope of tangent what? 3x square. Y coordinate y. 3x square equals to x cube. Since y equals to x cube. Curve, this is given curve. So we can write like this here. X cube minus 3 x square equals to 0. That is x square common, x minus 3 equals to 0. So we get x equals to 0 and 3. This two value we get. X equal to 0, x equal to 3. Now, for x equals to 0, from given equation, from 1 we get y equals to 0 q equals to 0. That is 0 0 is point, and for x equals to 3, y equals to 3, q equals to 27. Okay, if x equals to 3, then y equals to 27, 3 q. Hence, the points are 0 0 and 327, where slope of tangents is equal to the y coordinate. Y coordinate of point. Y coordinate of point. So, this is our solution. Take another question 23 of exercise 6.3. Here, prove that the curves x equal to y square and xy equals to k cut at right angles if 8k square goes to 1. That is, there are two curves. Suppose one curve is this, another curve is this. They are intersecting at this point. Two curves are cut at right angles. When we say that the two curves are cut at right angles, if two curves intersect at this point, then tangent at this point to the curve first and tangent of this point to the curve second. This is T1, this is T2. This should be perpendicular to each other. Clear? This should be perpendicular to each other. Then we say that the two curves are cut right angles. Okay. That means for finding the condition 8k square equals to 1, we will use the two tangents are perpendicular to each other. That is, two lines are perpendicular to each other. That means product of slope of these two lines, that is these two tangents, is equals to -1, because if two lines are perpendicular to each other, then their product of their slope is equals to -1. So we use this condition. So for that, first of all, we have to solve these two curve to get intersection point, and then at this intersection point we have to find the slope of the tangent to the curve, first curve by differential derivative. Similarly, slope of that second tangent to the curve C2 at that point. And then we use product of that 2 is equals to -1 and we can get the relation. Okay. So, let us solve it. Very, very important questions. So, note down it. Okay. Solution. Given curves are x equals to y square first and xy equals to k second. Okay. If these two curves cut at right angles, then we have to prove that 8k square equals to 1, our targeted value. Okay. So, first of all, we have to solve this two equation to get intersection point. To get intersection point of 1 and 2, we solve this. Xy equals to k, we have xy equals to k from 1, from 2, we have xy equals to k, implies y square into y equals to k from 1. In place of x, y. In place of x, y square. So yq equals to k. This implies y equals to k to the power 1 by 3. K to the power 1 by 3. Now, putting this value of y in this equation or in this equation implies x equals to y power 2, that means k power 1 by 3 power 2, that is k to the power 2 by 3. Clear? Y equals to k to the power 1 by 3 we get. Now y equals to k to the power 1 by 3, you have to put this value in 1 from 1. So x equal to this, y equal to this. So the point of intersection is x means k to the power 2 by 3 and y means 1 by 3. Okay, this is our point of intersection. Now we have to find the slope of these two curves at this point. Now the slope of tangent to the curve 1 is given by dy by dx from curve 1 This is curve 1. This is curve 2. Okay, this is curve 2. Curve 1. Okay. So curve 1, x equals to y square. Differentiate it on both sides with respect to x. 1 equals to 2y dy upon dx implies dy upon dx equals to 1 upon 2y. 1 left side 1, 2y dy upon dy by dx equal to 1 upon 2y, 1 upon 2y, and implies dy upon dx at the point k power 2 by 3 power 1 by 3. At this point, slope implies, suppose m1 is the slope, m1 equals to dy by dx at this point is equals to 1 upon, in place of y, 2k to the power 1 by 3. 2k to the power 1 by 3. Okay, this is m1. This is the slope of the tangent to the first curve. Similarly, we have to find the slope of tangent to the curve 2. Tangent to the curve 2 is given by dy by dx at C2. That is, so from second curve xy equals to k, differentiate both sides with respect to x, then we get x, derivative of x is 1 into dy upon dx. Derivative of x is 1 and dy by dx plus differentiate it with respect to dy dx of xy equals to dy dx of k, constant 0. Here, differentiation of first x means 1 into y plus first function derivative of second function equals to 0. That is, we get dy upon dx equals to minus y upon x implies m2 equals to dy upon dx at k power 2 by 3, k power 1 by 3 equals to, means derivative from second curve at this point. Okay, minus y by x. So minus in place of y, that is k 1 by 3 upon 2, x means k to the power 2 by 3. By solving it, k power 1 by 3, k power 2 by 3, 1 by 3 cancel. So this is equals to minus 1 upon k to the power 1 by 3. Okay. So minus 1 upon k to the power 1 by 3. 2 times 1 times so 1 time cancel out. Minus 1 upon. So this is m2, this is m1. These are the slope of the tangents to the curve at the point of intersection. Now, since this is m1, now since given two curves cut at right angles, that is at the point of intersection, tangent will be perpendicular to each other. That is m1 into m2 equals to minus 1. So put the value. M1 means 1 upon 2 k to the power 1 by 3 into m2 equals to minus of 1 upon k to the power 1 by 3 equals to minus 1. So this is equals to minus minus plus 2 k to the power 2 by 3. 2 k to the power 2 by 3 equals to 1. So squaring it. So squaring both sides. 2 k power 2 by 3, sorry, cubic. Cubic power on both sides. Taking cubic power on both sides, we can get 2 power 3 means 8. 3 3 cancel, k square equals to 1. So this is our result. Hence proved. Hence proved. Okay, 8k square equals to 1. So this is our proof. Okay.